In question 22, it says one of the fastest pitches recorded in the Major League Baseball was thrown by Nolan Ryan in 1974 and was clocked at 100.8 miles per hour. Now, this is certainly an out-of-date question, as there have been pitchers that have thrown much faster since 1974. However, let's continue with the problem. If a pitch were thrown horizontally with this velocity, how far would the ball fall vertically by the time it reached home plate? 60 feet away. Now, since the ball is curving because of gravity, we now have a brand new concept. It's no longer one-dimensional motion anymore. It's not straight line motion anymore. This is two-dimensional motion. And we have what is called projectile motion. There are two types of projectiles that you might remember. There are horizontally launched projectiles, in which we start off horizontal and we curve towards the ground. And there's projectiles that are launched at an angle, where it's launched up, it flattens out at the top, and then it comes back down towards the ground. In this example, this is known as a horizontally launched projectile. Now, something I want to focus on with regards to this concept is that when a projectile is flying through the air, there are no net forces pushing it or pulling it horizontally. Therefore, it has no reason to want to speed up as it's flying through the air. Once the ball leaves the pitcher's hands, the ball, horizontally speaking, represented by the blue arrows, is not going any faster nor slower. In other words, horizontal velocity is constant. Now, since it's curving to the ground, the gray arrows represent the fact that the velocity in the vertical direction is increasing because of gravity. So we're accelerating because of gravity in the y direction, but we're moving with constant velocity in the x direction. So it's always helpful to draw a picture. So we shall do that. Here's the ball. And it's going to end up somewhere down here. Now, since you are dealing with two concepts here, you're dealing with constant velocity in the x direction, and you're dealing with free fall acceleration due to gravity in the y direction, what we have here is we have two different concepts. Now, you might remember when we did constant velocity concepts, we listed three variables. They were x, v, and t. That was it. There was only need to list three variables for constant velocity motion. Now, for free fall acceleration, we listed six variables: y, y naught, v, v naught, a, and t, where a was equal to a negative g, and we replaced the number 10, or 9.8 if you wish, for the value of g. Now, since a projectile is a combination of vertical free fall acceleration and horizontal constant velocity, you're going to list a total of 9 variables: 3 in the x direction and 6 in the y direction. Now, technically, you're listing time twice, and the reason why is because time does not have a direction. So time is really found in all lists. And the reason I have students write it twice is so that students remember the time it takes for the ball to go 60 feet from the pitcher to home plate is also the same time it takes for the ball to fall, however much it's going to fall. So time is independent of direction. Now, what we do is we go back and we're going to add something to these variables to make them stand out and so that we can differentiate them in the x and y direction. Well, x and y are pretty easy. V, we're going to be writing as v naught x. In other words, this is initial velocity in the x direction. Initial velocity in the x direction. Over here, we have y naught, we have v in the y direction and v naught in the y direction. This would be the final velocity in the y direction. This would be the initial velocity in the y direction. Okay, and acceleration due to gravity, and of course time. Okay, so now here's what we do. Pretty helpful to label the picture. That way it can help you label your list, and then everything just comes together. Okay. Now, first thing I would do is I would start labeling some of the parts. So look at the information we're given. We're given 100.8 miles per hour. Now, we're going to have to convert that one. We're also given 60 feet. We're going to have to convert that one too. Well, it turns out that 100.8, if I want to go, let's say, from miles per hour to meters per second, I can use the following conversion factor. There are, in 1 mile per hour, there are 0.45 meters per second. And then for feet, I have to convert that to meters. So there are in 1 meter, there are 3.281 feet. Now, you never need to memorize these conversions. They're given to you. You can find them online, but you should know where to find them. So that might be the first thing I do is I'm going to take a look at this right here, and this has a value. That's my speed. Now, it's thrown horizontally, so this is going to be my V naught X. So my V naught X is the 100.8 miles per hour. However, we're going to multiply this by a conversion factor. We know that there are, in 1 mile per hour, there are 0.45 meters per second. Just move this down a little bit. And let me throw that into our calculator. .8 times 0.45 comes out to about 45.4 meters per second. Similarly, we need to convert the distance. The distance here is 60 feet, and 60 feet times the fact that there are 3.281 feet in every meter gives us about, we divide 60 by 3.281, it gives us about 18.3 meters. So we need to make sure we convert it into the right units, okay? Now, here's what I don't know. I don't know the time it takes to fall. Okay, I don't know that yet. Now, here's what I do know. If I find the time it takes to fall using a constant velocity equation, then I can use a second equation to find how far it falls from its initial position, given that same amount of time. So that's going to be our strategy. We're going to use two different equations. And we have to do that because we're moving in two different directions. So the first equation we're going to use is in the horizontal direction. We're using the equation x equals v naught x times t. This is the exact same equation as v equals x over t. The only difference is we've solved for x, and x equals vt. But instead of writing it as v, we're writing it as v naught x. So it's really distance equals velocity times time. It's your standard constant velocity equation. But I'm going to solve for time. So I'm going to divide by v naught x, cancels, and the time it takes to get to home plate would be 18.3 meters over 45.1 meters per second, and that's roughly about 0.406 seconds, something like that. Well, now what we can do is we can now use, for the vertical direction, a second equation. Now, to find how far it's going to fall, I can use the equation y equals y naught plus v naught t minus 1/2 gt squared. Now, the only thing I'm going to add to this is I'm going to add v naught y. Okay, it's the only thing I'm adding. Now, this is kind of important because when we go and we do our list here, something we should know. As we list our stuff, the time, I know the time is 0.406 seconds because I found it right here. It's the same time. V naught y is equal to 0 in this case, because if we look at the example, I start with velocity initial in the x direction. Notice the blue arrow is only going horizontally, therefore I have no initial velocity in the y direction. As soon as I'm, let's say, right here, now all of a sudden I have initial velocity in the y direction. It's very small, and it's going to get bigger and bigger and bigger. But initially, a horizontally launched projectile has no vertical velocity. Okay, and the final vertical velocity, I don't know it. My initial position, now here's the way we can work this one. You have to make a choice when it comes to y and y naught. If I choose to make y naught equal to 0, that means I'm falling. And if I'm falling, this value is going to be negative because I've dropped lower than 0. However, what I could do is I could make y naught my height, and I could find the level at which I'm falling to. So you kind of have to choose which way you're going to do it. I think this time I'm going to go ahead and call y naught equals 0. So if this is y naught is equal to 0, then this value here would be my y. And since I'm falling this, it's a negative value. So y is going to be your negative height, basically. Okay, so since v naught y is 0, I can cancel v naught yt. I can cancel y naught, and I can plug into the equation. Y is equal to negative 1/2 times 10 times 0.406 seconds squared. And that's roughly about 0.82 meters. In other words, as the ball falls, it's going to fall about 82 centimeters.